Hello, my name is Dr. Dayan Goodenowe, founder of Prodrome Sciences. I'm here to talk to you today about the plasmalogen hypothesis for the prevention of neurodegeneration and the treatment of impaired neurological function. Stop neurodegeneration, cure Alzheimer's disease. This is a project that we have in partnership with the EQ network. So the plasmalogen hypothesis is very simple. There's two parts. First part is that elevating blood plasmalogen levels to the 95th percentile or greater will prevent neurodegeneration. Second part is that elevating blood plasmalogen levels to the 95th percentile or greater will improve neurological function in persons suffering from a neurodegenerative disease. So I'm going to present to you in the following slides is the evidence that we've accumulated to date that supports these two hypotheses and the clinical trials that we will be performing to prove this in humans. The most recent studies that we worked on is large epidemiological studies. This is the Rush University cohort in Chicago, Illinois. It's a study that's been going on for 17 years. People enroll in the trial and they're cognitively normal and healthy individuals. And they participate in the trial till the end of their life. And when they die, they donate their brains and their organs to science, and the scientists study them. So time zero is the last clinical visit of the individuals. And since this trial has been going on for several years, some of those people are still alive, and some of those people have since died. Now we can go from the last clinical visit back 6 years and look at what's happened in the last 6 years of the individuals who've been part of this study. We've identified 1,262 participants in which we have 2 blood samples from the last visit and earlier. We look at the demographics, their age, their gender, genetic data like the APOE genotype, and a bunch of metabolomic data. So the overall summary of the patient population is as follows. The key aspects of it is an elderly population. Average age is 81 at visit 1, 85 at visit 2. Average time between visits is 3.7 years. So we have a delta. We can know people what's happened in their lives over a 3.7 year period of time. Robust cognitive distribution. NCI stands for no cognitive impairment. MCI is mild cognitive impairment. AD is Alzheimer's disease. And so of the 1,262 subjects at visit 2, 774 were still cognitively normal. 302 subjects had mild cognitive impairment, and 186 individuals had Alzheimer's dementia. So we have a very robust distribution of cognitively normal all the way through to demented individuals. And what's important is that if we look at visit 1, there were 77 cases of dementia, and at visit 2, there's 226 cases. So we have 149 new cases of dementia that have occurred in the follow-up time. So we can look at what was the characteristics of those individuals who were not demented at visit 1, but became demented in the years intervening between visit 1 and visit 2. For those individuals who are deceased in the study, the average time to death from their last clinical visit was 1.6 years. So we can actually look at the mortality analysis. So when we look at plasmalogen levels, so plasmalogens are a phospholipid that your liver makes that gets transported to your brain. So it's a blood test. We measure it. So it's a continuous distribution. There's people with low levels and there's people with high levels. So the first thing we can ask is, what is the incidence of dementia in individuals according to the level of plasmalogens in their blood? And what this graph shows is that the median level, the middle, each of these bars is 1 standard deviation. And it says that for each standard deviation increase in plasmalogen levels, the incidence of dementia goes down by 2, by half. So roughly 14% down to 7.5% to 4.3%. So people with high levels of plasmalogens have a very low rate of dementia, whereas people with low levels of plasmalogens have a high rate of dementia, and it's continuous. And if we look at that differently, we look at all of the variables in the study, we can identify people with low plasmalogen. So PBV stands for the plasmalogen biosynthesis value. It's a composite of plasmalogens in the blood. People with very low levels, and people with very high levels, so the 95th percentile level. So if we look at individuals that are 85 years of age, people that had high levels of plasmalogens only had roughly 5% rate of dementia, 85-year-olds. The average rate of dementia in the 85-year-olds was around 15%, and if you had low levels of plasmalogens, it was up to 30%. So here it's very clear, and these error bars here are the 95% confidence intervals. So this graph shows with a high degree of confidence that high levels of plasmalogens are associated with low rates of dementia in this population, and low levels of plasmalogens are associated with high rates of dementia in the population. The other thing we can look at is what's the relationship with plasmalogens with advancing age? And if we look at, we did 2 studies, both of which had about 1,000 individuals, so very large powered studies, from age 30 to basically age 90. And this indicates that the levels of plasmalogens in the general population decrease with increasing age. Now, the interesting thing also is that these are from Ohio, United States, and in Canada. The blue and the red here are actually both males. So males in both populations have slightly higher levels than females, but the rate of decline is similar in both males and females. This actually could be one of the explanations of why females get dementia at an earlier age than men. Now, this graph shows the average level, but that's not the true individualized level of plasmalogens. When we take averages, so for instance, if you have 1,000 people at age 30, not every one of those people has the same 2%, 5%. They're not all having decreased levels of plasmalogens. What happens is you have a group of people that the plasmalogens never decrease. They're normal the whole time. But what drives the average down is that you get more and more people that have low levels. So the question we can ask, is, although the population average decreases, there's 10% of people that actually have levels in their old age similar to what they had when they're younger. And so we can ask the question, what's different? What's the incidence of dementia in elderly persons that do not have an age-associated decrease in plasmalogens? And we get some pretty interesting information. So this is the large study. So when you're looking at longitudinal 6-year time to dementia analysis, we have to start off with individuals that don't have dementia. So everyone at starting point, so the dementia line is zeros all the way down. And we're looking at the top 10% of the population, about 123 individuals. And we tracked them, so everybody started with no dementia, so 100% normal at time 0. And we tracked them over time, over 6 years. And what you can see is people with high plasmalogens didn't get dementia, very little rate of dementia. And for comparison, the largest genetic risk factor for Alzheimer's disease is the ApoE4 genotype. And so you can compare the rate of dementia in the genotypes versus the plasmalogens. And you can see that the plasmalogen effect is much stronger than the genetic effect. So this is pretty cool. So what happens is we know how many cases, if this was completely randomly distributed, we would expect in those 123 people to have 30 cases of dementia. But we only found 6. So in the high plasmalogen population, there was an 80% lower rate of dementia in this population than was expected by pure chance. That's a very powerful number and a very highly significant. 2.1 times 10 to the minus 6 is 2 chances in a million. So since we also know people were dying eventually because they're the elderly, we can ask the question, what's the relationship between plasmalogens and mortality? And what this shows is that people with high plasmalogens in their blood at baseline, at visit 1, had a 50% or more than 50% lower risk of dying. So these odds ratios are, for each standard deviation increase, what your probability of an event is. And so 1 standard deviation higher plasmalogen levels at visit 1 reduce the risk of dying by more than 50%. And if your plasmalogens increased in that time, your risk of dying also was reduced. However, if you had dementia at your last plasmalogen visit, you were more likely to die. So dementia itself is a risk factor for mortality. So these are pretty scary numbers. And if you graph it, we go back to the similar 85-year-old, okay, and this is age at visit 1. So the average time up, we're talking about over the next 5 years. Mortality in 85-year-olds with high levels of plasmalogens over the next 6 years was less than 20%. But in people with low plasmalogens, it was upwards of 70%. So we're dealing with extreme correlation with mortality as a function of the plasmalogen levels in their blood. So take-home message is, low plasmalogens are bad, but that doesn't necessarily answer the question that we want to answer is, if we correct this, does it cause a benefit to anybody? So the question is it causation or is it coincidence? And causation and coincidence is basically like the smoke of your automobile. Okay, so if the piston rings in your car break down, you get a bunch of black smoke coming out of the back of your car. And so the black smoke is basically a biomarker of impaired engine function. But you wouldn't say that the black smoke coming out of your car actually caused the pistons to go down. Like, you wouldn't be able to put a filter on the back of your car and say, oh, if I can just hide this smoke from the world, my engine is going to just miraculously start working normally again. No, because that's just a coincidence of engine failure. So now we have to ask the question, these plasmalogens, are they somehow involved in the disease causation, or is it just a coincidence that they are well associated with mortality and dementia? So let's talk about the neurodegeneration. So plasmalogens and the prevention of neurodegeneration. One of the models we use is Parkinson's. It's the MPTP model of Parkinson's. So MPTP is a neurotoxin that was created by kids that were trying to create a novel form of heroin, actually, MPPP, which was not regulated by the FDA, so they could actually get the drug and not be illegally using it. And one of the toxic byproducts was this MPTP. And it turns out that when they made their drug wrong, they gave themselves Parkinson's. And so ever since then, in the 80s, we now have had a toxin that we use for studying Parkinson's. So MPTP comes into, this is a dopaminergic neuron. DAT stands for the dopamine transporter. VMAT stands for the vesicular monoamine transporter. So dopamine is a monoamine. And so MPT comes in here, it gets concentrated in these presynaptic vesicles and eventually kills dopaminergic neurons. So it's selective to dopaminergic neurons. And how we study this is we say, okay, if we can treat mice with plasmalogen precursors and elevate plasmalogen levels in the mice, so we treat the mice with the plasmalogen precursors at day 1. We give them 5 days for the plasmalogen levels to get up. Then we administer the dopamine neurotoxin, MPTP. And we let the toxin take its normal course, and then we measure whether or not plasmalogens had any effect on the toxicity of this well-known neurotoxin. And the results are as follows. So control animals on MPTP, this is serum levels of plasmalogens. So interestingly, MPTP actually seems to be a little bit of a liver toxin as well, because it lowers the serum levels of plasmalogens. And we looked at 5, 10, 50, and 200 milligrams per kilogram dose of a plasmalogen precursor. This is the dopamine transporter, and this is the vesicular transporter. And what you can see here is that at 50 milligrams per kilogram, which is actually a fairly reasonable dose, we get 100% protection of neurodegeneration in this animal model. So clearly the plasmalogens are neuroprotective. A second model we studied was the Cooperzone model of neurodegeneration. So Cooperzone is a copper chelating molecule that was discovered that can cause demyelination, which is the white matter. So myelin is the insulating sheath of your neurons in your body. And if that gets degraded, typically through inflammation, you get a disease called multiple sclerosis. And what happens is, if you administer Cooperzone to mice over time, around 6 weeks, you see a very large amount of degeneration, about 50% degeneration of the neurons. And if we treat the animals, so a regular diet, this is what a nice, healthy neuron looks like with good myelination. Cooperzone treatment, you see this whole cellular structure is basically gone. This is a picture of demyelination. And if we administer the plasmalogen precursors with the Cooperzone, we completely prevent demyelination caused by Cooperzone. So basically, plasmalogens prevent neurodegeneration in 2 separate neurotoxic models. So the answer, causation or coincidence? Causation. Now, in terms of neurological function, function and pathology are 2 different things. Pathology is the physical measurement of the structure of the brain. Function is the measurement of whatever is remaining, how it's actually working. Is it functioning or not? So plasmalogens, what they are, they're phospholipids. And so phospholipids have a hydrophilic head group, hydrophobic tail, and they create what's called a phospholipid bilayer, which is a membrane. So our entire body is made up of membranes. Membranes is what separates cells from each other. It gives us the physical structure of our body and everything. So and these cell membranes can be fluid, they can be rigid, they have different types of, they're very diverse membranes. So the plasmalogens are one of these type of molecules. And neurotransmitter release and function occurs following. So typically there's a neurotransmitter, there's a action potential that is propagated in a neuron that causes the presynaptic vesicles that contain the neurotransmitters to fuse and release the neurotransmitters. And the neurotransmitters come down and they connect to the postsynaptic membrane, and that's how a neuron propagates a signal from one neuron to the next. This process here is the vesicular fusion process. So it's a biophysical process where a vesicle containing millions of neurotransmitters physically fuses and releases their contents into this synaptic cleft. It turns out that that process is heavily dependent on plasmalogen composition. And not just any kind of plasmalogen, very specifically polyunsaturated plasmalogens. So if you change the polyunsaturated state from arachidonic acid, in this case, to oleic acid, membrane fusion dramatically goes down. And if you change the plasmalogen backbone to a phosphatidyl backbone, it goes down. So not to get into great details, plasmalogens are a very unique phospholipid that has a very special bond called a vinyl ether bond at SN1. It gives it special physiochemical properties. The point of the story is that plasmalogens are necessary for membrane fusion events to occur. And membrane fusion of released transmitter is how neurons function. So to measure function, we did a study called in Parkinsonian monkeys looking at L-DOPA-induced dyskinesias. So L-DOPA is the primary drug to treat Parkinson's, and it's pretty well a miracle drug because it restores dopaminergic function in individuals with Parkinson's. The problem is, over periods of time, after long treatment with L-DOPA, people end up getting what's called dyskinesias, which are abnormal movements, not the shaking and tremor that are traditional with Parkinson's, but abnormal movements. And so these are monkeys in which the neurons have actually already been lesioned, so they're dead. Like the dopaminergic neurons, 85% of them are gone, so they're not coming back. And we found that we treat these monkeys with the plasmalogen precursors. After only 2 days of precursor treatment, we had a dramatic reduce, like a significantly reduced level of dyskinesias. So here's another observation where the plasmalogens are actually physically doing something. They're not just bystanders at an accident. So in terms of function, causation or coincidence, causation. Now, Alzheimer's disease, there's three main pathologies for Alzheimer's disease, and this is what most of you will have some level of experience if you Google Alzheimer's disease. There's the three main things that we see in postmortem brains of individuals with Alzheimer's is that we see shrinkage. The brain's actually smaller, and this is due to lipid degradation. They have tangles. Tangles are tau. They form inside the neuron, and amyloid plaques, which people hear beta amyloid, they occur between the neurons. And what's important to note is that pathology doesn't necessarily correlate with cognitive impairment. So here's a study that was done in 2005 by Bennett's group at Rush University. And basically, if you separate the functional characteristic of the disease with the neuropathological characteristic of the disease and say, if you get a neuropathologist to diagnose Alzheimer's disease without having any knowledge of their cognitive state, 55% of people that have no cognitive impairment the neuropathologist will diagnose as having Alzheimer's disease. And so clearly, pathology is not completely deterministic of function. So clearly AD pathology is not causing dementia. But let's talk a little bit about amyloid, because we still shouldn't have it. So the formation of amyloid and the accumulation of amyloid is not a healthy thing. It is a biomarker of abnormal brain function in some way, shape, or form. There's some reason why amyloid is accumulating that shouldn't normally accumulate. So let's ask that. So the formation of amyloid goes through a molecule called amyloid precursor protein. And there's two enzymes. One's beta secretase and one's alpha secretase. And these enzymes chop up this APP molecule in two different parts of the molecule. If APP gets metabolized by beta secretase, then we end up with these amyloid beta fragments, and this is the one that causes the amyloid plaques in the brain. If it gets processed by alpha secretase, we don't get any amyloid plaques. So alpha secretase is the healthy processing, beta secretase is the unhealthy processing. It turns out that these two enzymes don't live in the same place. As I mentioned to the membranes are very diverse. Membranes have, almost like a city, you'll have ghetto areas, you'll have suburb areas, you'll have downtown areas, and there's different activities that occur in different areas of the membrane. The beta secretase molecule is in the cholesterol-rich region called lipid rafts. It's a very tightly packed structure. So it likes to be in the tightly packed lipid structure. Whereas the alpha secretase exists in the phospholipid-rich region, which is a much more fluid region. And so we can actually study the effect of plasmalogen modification of amyloid formation by providing precursors. So this molecule is a DHA plasmalogen precursor. So we can selectively increase the polyunsaturated composition of membranes. And when we do that, and in dose-dependent manner, what we see is soluble APP, which is the product of alpha secretase, goes up with increasing DHA plasmalogens. More importantly, is that increasing the plasmalogen composition of the membrane dose-dependently reduces amyloid beta 42 levels. If we use cholesterol, which is the opposite, which causes thickening of the membrane, we get an increase in A beta 42. So here you have a very strong relationship of how we can manipulate. If we change the membrane composition, we actually change beta amyloid formation. Now this is pretty cool in cell culture. Does this actually happen in humans? So to ask that question, we did post-mortem brain analysis of 100 individuals with a nicely diverse cognitive status, 38 cognitively normals, 24 with mild cognitive impairment, 38 with Alzheimer's disease. We did a bunch of analyses in different brain regions. We looked at tangles and amyloid and plasmalogens and other phospholipids and transcripts. So it was a very comprehensive study. But one thing in particular we want to ask is there a relationship between brain plasmalogen levels and brain amyloid levels? So we asked the question with the outcome as being brain amyloid. And so here we have amyloid levels in people with high plasmalogens versus normal plasmalogen, like low plasmalogens. And in human brain, we see exactly what we saw in the tissue culture lab, in that individuals that had high plasmalogens in the brain had low beta amyloid in the brain. And in fact, high levels of plasmalogens counteracted the effect of the ApoE4 genotype in formation of amyloid. So in terms of the what's driving beta amyloid accumulation, causation or coincidence, causation. So beta amyloid formation is due to membrane structure dysfunction. Now, one of the things we do is we look at these associations, and we try to determine which associations are causal and which are just coincidental. And the way you do that is you look at multiple variables. And if we do that with all the things that we measured, we found that the DHA plasmalogen had the strongest association with cognition of any neuropathological thing. And what's interesting is that the odds ratio in the brain is much larger than the odds ratio in the blood. So the previous slides showed you that the odds ratio was around 0.5, which meant one standard deviation increase in plasmalogens in the blood reduced your risk by twofold. So you went from 100% to 50%. In the brain, it's a 5 times. So it's the association of plasmalogens in the brain are much stronger than the association of your blood plasmalogen levels, which you would expect because your brain levels are more proximate. They're close to the actual cause of neurodegeneration and cognitive impairment. So plasmalogens, which is a phospholipid-rich region, flotilin, which is a biomarker of the cholesterol-rich regions, which is the lipid rafts, choline high-affinity transport is a biomarker of cholinergic neurons. Basically, the more cholinergic neurons you have, the less dementia you have. And then tangles came in at the end, which is one of the biomarkers for Alzheimer's disease. So then if we look at the interaction map of all these things, we can say that ApoE4 was associated with increased levels of amyloid. And so once you understood the levels of amyloid, E4 was no longer significant. And then, so this is an interaction map that we try to get to use to determine the relationship between association and causation. The example I often use for people is something different than what we do with neuropathology, is something simple. Say someone said that, oh, women have 5 times higher rates of scalp irritations than men. And well, that's interesting. So what's causing that? Was it is it the hormone difference in males and females? Like what's different about females that give them higher head rashes? And then some guy later on says, oh, you know what? If you look at hairspray usage, and because 5 times more women use hairspray than men. So if you only compare women who use hairspray with men who use hairspray, now all of a sudden there's no difference. The rate of scalp irritations is the same. So now you can say, so it's not about being male or female, it's about whether or not you use hairspray or not. Then you can ask the next question, well, is it all hairsprays or is it just some hairsprays? And then so if you start looking into the different types of hairsprays, then you say, it's only brand X. Okay, it's only people who use brand X that get the scalp irritations. All these other brands of hairspray don't have an effect. So it's not all hairspray, it's very specific hairsprays. Then you can go one step further and say, well, what is it in the hairspray? Is it a specific compound in that hairspray? And so maybe there's compound X in that hairspray, and then you realize by this association, when you go from females to hairspray to a brand to a chemical inside that hairspray. That's how we take these associations and understand causation. Doesn't mean the associations are never real. Even after you've identified the causative agent, the original association is still true. Females are still having 5 times higher rates of skin irritations. We just know the cause of it. So same thing happens here. ApoE4 is the strongest genetic risk factor for Alzheimer's disease. It's virtually the strongest acquired risk factor of almost any disease. However, if we know the amyloid level of the person, the E4 is no longer significant. So it's only E4 carriers that have high levels of amyloid that have an increased risk of Alzheimer's disease. So once you know the amyloid level, E4 no longer becomes a significant association. And then if you look at amyloid and tangles, if you know the tangle levels, amyloid is no longer significant. And you get down to the point where at the end, these four things ended up having, we couldn't eliminate them. They became independent. They had their own association with cognition. And this is why, when you look at these maps, you can understand why the amyloid hypothesis was very unsuccessful in treating Alzheimer's disease, because it really wasn't, in the cascade of things, even statistically causative. So, in summary, we have two clinical trials that we're going to be executing. This is the University of Pennsylvania trial. It's a public-private collaboration. University of Pennsylvania, Dr. Mitchell Kling is going to be running the trial. He'll recruit and administer our plasmalogen precursors. The Alzheimer's Association is providing all the funding for the trial. Prodrome Sciences, we're going to manufacture the plasmalogen bioprecursor, and we'll also do all the biomarker analysis of plasmalogen levels and so on. We've already begun manufacturing the plasmalogen precursor, and the enrollment, we believe, will begin in early 2020. The purpose here was to evaluate the utility of using plasmalogen precursors on blood and CSF levels. So we want to understand how elevating plasmalogen levels affect other biomarkers. Look at cardiovascular and pathology markers, and we'll look at cognition. In parallel with the University of Pennsylvania trial, we're initiating a very large community-based trial with EQ. And purpose of this is a clinical trial called the SAS trial, and it's an innovative and transparent product development and global access ecosystem. Our goal here is to take an innovative product, which is the plasmalogen supplement program, and create a distributive clinical model, community model for the testing of new products like this. So Prodrome Health Center is going to recruit the participants and administer the plasmalogen precursor. EQ will create a proxy participant crowdfunding model. Physically it's a trial, so it actually physically has to exist in a geographical location. We're not doing the trial all around the world. But the EQ partnership will allow us to have proxy participants, so people can be part of the trial or finance part of the trial, and in exchange for product, early access to the product, and also exchange for a return on investment for the success of the distribution model of the clinical trial itself. The whole part of the EQ network is to create a sharing ecosystem that can better match product developers like ourselves and clinical communities that we're developing in the clinical trial community, and investors and developers through the tokenization of the financing model. Prodrome Sciences will manufacture the plasmalogen and do the extensive biomarker analysis. Again, manufacturing has begun. We're hoping to start the pre-enrollment at the end of this year. We're looking at around 5,000 people over the next couple of years, so a very large trial. We're expecting our first outcome analysis around the middle of 2020, third quarter. And the purpose will be evaluate the utility of our plasmalogen precursors on neurodegeneration and neurological function. So that is the short story of the plasmalogen hypothesis and our intention of testing it in the real world. Thank you very much for your attention.